Rethinking a Wheeler-Gedanken experiment. Greetings. I'm Louis Little. I'd like to introduce you to Jeff Boyd.
Thank you, Louis. So, my purpose in this video is to take one of the classical experiments of quantum mechanics, one of the experiments that convince people that as bizarre as it is, quantum mechanics must be true, because look at the experimental evidence. I'm going to take this experiment and explain to you how the experimenters understood what they were doing and arrived at their conclusions, and then demonstrate that by starting from different starting assumptions, starting with a different theory, we arrive at drastically different conclusions. The experiment in question is Jacques et al., published in Science in the year 2007, Experimental Realization of Wheeler's Delayed Choice Gedanken Experiment. Now, Gedanken is, of course, a German word meaning thought experiment. Now, the experiment by Jacques et al. Started in a historical tradition way before John Wheeler. It started with Louis de Broglie, who in his PhD thesis of 1924 said any moving particle or object has an associated wave. And that idea inspired in others the concept of wave-particle duality. Wave-particle duality means that you have a wave particle. It can be observed as if it were a wave, it can be observed as if it were a particle, but it's two aspects of the same thing. Now, assuming that wave-particle duality is true, John Wheeler designed an experiment in which the wave particle had to behave and be observed one way or the other. If you take a photon quantum and put it into an interferometer down here, according to Wheeler, it can go through the interferometer as a wave on both channels. The way we know that it's a wave is that there's interference up here. The one coming across this path and the one coming up this path interfere. Or it can decide to be a particle and it can go this way and then hit detector D2, or it can go this way and hit detector D1. So, we're trying to find in this interferometer, is it a particle or is it a wave? Now, the thing is that it turns out that there's a very strong correlation between how we look at the particle and how it behaves. If we're looking for a wave, then way back here at the entrance to the interferometer, it will behave like a wave. And if we're looking for a particle, way down here, it will decide that it's a particle. So how do the detectors communicate with the photon quantum that's entering the interferometer? Wheeler said, well, look, let's have delayed choice. By that he meant that first a photon quantum would enter an interferometer, and then as it enters, it would make a commitment to go this direction as a particle on path 1, this direction as a particle on path 2, or both directions as a wave. Now, it's made its decision, and then as it's traveling, while it's in the interferometer, then after it's entered the interferometer, then we will decide which kind of detector we will use. Is it still the case then that the kind of detector affects or causes a different kind of photon? It's an interesting question. Now, Wheeler describes his interferometer as having two configurations. If there are detectors D1 and D2 for particles to be detected, that's called the open configuration. If there's a mirror up here so that you can see interference, that is called the closed configuration. Now, Jacques et al. Set about to build exactly the experiment that Wheeler described. The way they did it was that they had an interferometer that was 48 meters long. So it takes a photon quantum 160 nanoseconds to get across it. And then they had a switch up here, something called the electro-optical modulator, EOM, which would at random turn on or off in 40 nanoseconds after the photon had entered the interferometer. And what the data is going to lead to, which I'll tell you in a minute, is that whichever way you decide to look at it, that's what it is. If your detectors say that we're looking for a particle, then the photon will behave like a particle. If our detectors say we're prepared for a wave, then we will find a wave. So how is it that way back here at the entrance to the interferometer, the photon made that decision? What we're going to find from this experiment is a conclusion, from Jacques' point of view, that this is the cause. Whatever is decided up here determines what the photon is going to do. This is the effect which occurred earlier in time, backwards in time causation. This is the model I will discuss in this video. It's very similar to the experimental apparatus that Jacques et al. Used. It's slightly simplified in the area of polarization, but the essential features are the same. Now, when I've presented these ideas about Jacques' experiment at the American Physical Society, most people in the audience have told me that they don't really know what the experiment was. They need to be reminded of the details. So that's what we're going to do. We're going to briefly introduce what the experiment was from the point of view of quantum mechanics, from the point of view of the experimenters. And then when we're done with that, we will rethink the whole thing based on different premises, different assumptions. In the Jacques et al. Publication in Science in the year 2007, this is called an open configuration of the equipment, and this is called a closed configuration of the equipment. This red dowel, and any red, will represent a vertically polarized path or wave or photon, and the blue one will represent a horizontally polarized path or wave or photon. So here's what the experiment consisted of. Over here, the experimenters remarkably put in a single photon quantum. It's amazing that they could do that. Now, from their point of view, here's what happened. The quantum went in here and it decided inside this beam splitter here whether to go this way as a horizontally polarized photon, this way as a vertically polarized photon, or as a wave across both channels simultaneously. It then went into a reverse beam splitter, which combines the two, the vertical and the horizontal, into one output here, which is both vertically and horizontally, but they're not mixed up. You can distinguish them. Then the signal goes into an EOM, an electro-optical modulator, which, when it's turned off, as it is here, acts as if it were not present. It then goes into a Wollaston prism, WP, and the Wollaston prism assigns it, if it's horizontally polarized, to detector D1. My model fell apart. And if it's vertically polarized, which is red, to detector D2. I can easily put the model back together. So this part over here is called the output area, and that's where really all the action is, from my point of view. Except for the timing of the input of a photon quantum, the experimenters have only two variables that they can control in this experiment. This is the reverse beam splitter, and one variable is that it can be tilted this way and that by a step motor, which, if it were a wave coming across the interferometer, this tilting back and forth of the reverse beam splitter causes a phase shift in the waves from the upper versus the lower path coming across the interferometer. So there is a phase shift in the two waves, and that is then rotated as they come across this device. And at the entrance to the Wollaston prism, there is interference. The second variable that the researchers can control is whether this EOM is turned off, which is it is here, or on, which I've painted with stripes. That's not how they think of it, but it's how I think of it, because if it's turned on, it has the effect of rotating the angle of polarization of the incoming waves by plus 45 degrees, or pi over 4. When it's on with these stripes like that, that's the orientation for seeing wave interference. When it's off like that, that's the orientation for seeing particles but not being able to see wave interference. So this variable, the EOM being turned on or off at random, can occur very rapidly in a matter of 40 nanoseconds, and can occur after the photon has already entered the interferometer and made a commitment to going this way as a particle, this way as a particle, or both paths as a wave. Keep in mind that you can only see wave interference if the EOM is turned on, because what the EOM does is it takes the phase shift from this device and twists it so that it becomes interference over here. If the EOM is turned off, there will be no interference over here, which is why you see no interference. Nevertheless, there can still be waves, and there can still be a phase shift generated by this device tilting. Now, all output data, all the data from this experiment comes from detectors D1 and D2. From their point of view, if the photon quantum is coming across the interferometer on both beams because it's a wave, and it enters that reverse beam splitter, the blue thing, which is being tilted a bit this way and that to produce interference of the upper versus the lower wave, and if it then goes through that EOM turned on, what you will find in the final detectors, in the final data set, is that over time, the amount of photons detected by one detector versus the other goes like this. And that's how you know that there is interference, because depending on which angle you set for the reverse beam splitter, you'll get a different distribution of the number of photons per second at D1 versus D2. If, on the other hand, from their point of view, the photon is a particle coming across the interferometer on either one of the paths, and the reverse beam splitter, the blue thing, is tilting, then it will go through and the detectors will detect the same number of photons approximately on each side over time. And that's how you know there is no wave interference. And from Jacques' point of view, they incorrectly infer that that means that there were no waves. In the actual experiment, the reverse beam splitter moves slowly from one extreme to the other. The reason I have presented it as rocking back and forth is that I wanted to make a more interesting and dramatic video. So here are the primary results of the Jacques et al. Experiment. A photon quantum comes in, and it will take 160 nanoseconds to traverse this 48 meters. Meanwhile, at random, and within 40 nanoseconds, the EOM is turning on or off. So the photon has already made its commitment, apparently, and if the EOM is turned off, expecting a particle, that's the orientation of this thing to detect a particle, then the photon behaves like a particle. If, on the other hand, at random and during the flight of the photon, somewhere in here, you're expecting a wave, which is what this EOM turned on, that's how you detect a wave, then what do you know, the photon behaves like a wave. So whatever you're expecting, that's how the photon behaves, even though the photon was making its commitment long before the random numbers decided which way this EOM was going to be oriented. It appears as if this is the cause and this is the effect which occurs long before the cause. Strange. Now, assuming that wave-particle duality is true, we learn from the Jacques experiment that leads us to the idea that time goes backwards, i.e. a cause can occur later than its effect. There are also various other explanations of this experiment, none of which make any sense. So what's wrong? Well, if you're open-minded, you might consider the possibility that what is wrong is the starting assumption about wave-particle duality. If wave-particle duality is not true, then this cascade of ideas and this experiment would kind of fall apart. We'd have to think about it in a different way. Now, if we take off the blinders of wave-particle duality and look at the experiment for what it just plain says, what does it say? Well, what it says, obviously, is that if you're looking for waves, you see waves, and if you're looking for particles, i.e. photons, you see photons. Obviously, they must both be present all the time, or the experiment would not make sense. I mean, there's no evidence here of wave-particle duality. Someone might object that there is a contradiction in what I just said. We are putting into the interferometer down here a single quantum of photon-like energy. How is it possible that a single quantum could become both a photon and a wave when there's only enough energy for one or the other? Our theory would be this: one quantum does not become two things. Each quantum becomes a photon. There are always waves, always. They convey no energy. The quantum, the photon, follows waves. Thus, if you're looking for waves, you'd find waves. If you're looking for photons, you will find photons. Imagine, if you will, that I have a specialized camera with two lenses, and the only way I can know reality is through this camera. One lens sees only women, the other lens sees only men, and I can change the lenses back and forth very quickly. So I go into New York City during rush hour, and I look at the sidewalks through my camera, and all I see is women. And then, with my eyes closed, because I can't see anything except through the camera, I switch the lens and look again, and all I see is men. And I do it over and over, and every time, if I look this way, I see women. If I look this way, I see men. And so I say, look, this is incredible. Somehow the men are changing into the women, and the women are changing into the men. So then you say to me, well, look, can you change your lenses faster? Maybe if you changed from this lens to this lens and back in 40 nanoseconds, then you'd really be able to see what's going on. And so I try that, and what do you know? When I look through this lens, I always see women, and when I look through this lens, I always see men. Now look, I can change lenses in this camera in 40 nanoseconds much faster than light can reach my camera from those people over there. So do you think that the logical conclusion of this experiment is that my choice of lens causes, backwards in time, those people over there to make a decision whether to present themselves to my camera as a man or a woman? Returning to the Wheeler-Gedanken experiment, we invite you to build your own theory to explain this experiment. Here's what I think are the lessons that this experiment teaches us, and which would have to be the foundations of a new theory. First, that every time a detector clicks, it's because it is struck by a photon. That waves are everywhere. One quantum of energy put in down here has enough energy to make one photon, which, if they're always waves and photons, leaves no energy left over for the wave. So the waves must convey zero energy, which contradicts what other waves are like, but it seems to be true of these waves. That photons carry all the energy and momentum, and that every photon is associated with a wave. And if that's true, then you have to figure out whether polarization is carried by the wave or the photon. I think that those are the minimum criteria or foundations upon which you should build your own theory. Now, I'm not saying that our theory, which I'm about to show you, is correct or better than the theory you will build, but I think it might inspire you to build your own theory if you see that we've made an effort in that direction ourselves. Our theory is that we are surrounded by, we are immersed in an ocean of elementary waves. At all points in space, they go in all directions at all wavelengths, and they are subject to wave interference, and they convey no energy. Particles follow them probably backwards. In summary, the purpose of this video has been to demonstrate that quantum mechanics is not the only way to understand this experiment by Jacques et al. The entire experiment grows out of the concept of wave-particle duality, and if we stop thinking that way, if we don't accept the idea of wave-particle duality, then we arrive at an entirely different view of the experiment, in which it's easy to understand why, if you're looking for waves, you see waves, and if you're looking for particles, you see particles, because in reality, there are both waves and particles, and they are not two sides of the same thing. That is our main point. One of the primary reasons that this study by Jacques et al. Is so famous is because it shows that although people previously thought that quantum mechanics was weird, this study shows that quantum mechanics is far more weird than anyone had previously imagined. Now let's talk about weirdness. There are two different kinds of weirdness. There's sort of a finite kind and another kind that keeps doubling and doubling in size. The ideas of Einstein about relativity are, in my view, weird. I mean, for example, I still find it very strange that two events can happen simultaneous, and from another frame of reference, they are not simultaneous. That's weird. But it's kind of a finite weirdness. If I accept that level of weirdness, then things make sense, and after that, there's no further weirdness beyond the beginning weirdness. Now, things are different than that in quantum mechanics. There is weirdness, and then people do an experiment to explore the weirdness, and they find it even weirder than that, and every year or every decade, the weirdness doubles in size. This latter type of weirdness is the type of weirdness that you would expect if an error had been made, if a mistake had been made way back at the beginning. For example, the idea of wave-particle duality was, in my view, a mistake. Now, if a mistake is made in a theory early on and people can't figure out what the mistake was, Then as you do more and more research, you find more and more flaws, more and more discrepancy between the theory and your experiments in reality, and then you have to invent more weirdness to fill in that gap and to wallpaper over this contradiction. And I propose that that is the type of weirdness found in quantum mechanics. It's doubling and doubling in size. If you think it's bad now, I predict it'll be much worse 10 or 20 years from now. It's much easier, in my view, to start with the Jacques experiment, and instead of arriving at the conclusion that people do arrive at, namely things like, well, quantum mathematics is outside of space and time, and it's quantum mathematics that is in control, and in fact there is no real space and time at the quantum level. The reality, physical reality, does not exist. The world is really all mathematics. Forget that. I mean, let's go back to the original problem, which was wave-particle duality, an idea that was accepted without really thinking about the alternatives. It's better to fix that, in my view, that original error. Thank you very much for your time and attention.